Alright, let's take a look at this geometry problem. We are exploring rotations, which is just a fancy math word for turning a shape around a fixed point. In this question, our fixed point is the center of the square, where the x and y axes meet, and we are rotating counterclockwise. This means turning to the left like the opposite way a clock moves. Let's look at part A. It is asking to find which diagram represents a 1/12 counterclockwise rotation. First, we need to figure out what 1/12 of a rotation actually looks like in degrees. Now, a complete turn all the way around is 360 degrees, which is a full circle. To find 1/12, we divide the full circle, 360 degrees, by 12. This is going to be equal to 30 degrees per part. We are looking for the square that has been nudged once only to the left, as 1/12 means moving one part only. And counterclockwise indicates the direction of the movement, which is left. Looking at the options, the first option is the right answer, because you can see that the square rotated one part only to the left. Moving on to part B, the question is asking to find the diagram that has a 90 degrees counterclockwise rotation. Now let me start with the property of a square. A square is very special because all its sides are equal and all its corners are 90 degrees. Because a square is perfectly balanced, if you rotate it by exactly 90 degrees, it lands right back on top of where it started. It will look identical to the original image. So, looking at our options, we have to find a square that looks exactly like the original, since we are looking for a 90 degrees turn. Obviously, the second diagram is the correct one, as it is identical to the original image. Thank you for watching, and see you in the next video. Alright, let's take a look at this geometry question together. We are dealing with rotations, which is basically just another word for turning a shape around a fixed point. In this case, we have a regular hexagon named PQRSTU. Since it's regular, we know that all its sides are the same length and all its central angles are equal. Okay, let's think of this hexagon like a pizza cut into 6 equal slices from the center O. Now a full circle is 360 degrees. Since there are 6 equal sections, then each slice, like the angle from R to Q, is 360 degrees divided by 6. This is equal to 60 degrees per section. You can even see that 60 degrees angle marked on the diagram. Now the question tells us the hexagon is rotated 120 degrees counterclockwise. This means that we are turning to the left. So, if one jump from one letter to the next is 60 degrees, how many jumps is 120 degrees? We say 120 degrees divided by 60 degrees, this is equal to 2 jumps. So the image is just where a point lands after the turn is finished. Let's find point U on the left side of the hexagon and move it 2 spots counterclockwise. Starting from point U, we do our first left jump, which is equivalent to 60 degrees. We are going to land on T. Since 120 degrees is equal to 2 jumps, therefore, let's do our second jump, again to the left, and we are going to move from T to S. Therefore, the image of U is S. Thank you for watching, and see you in the next video. Alright, let's take a look at this geometry question. We are going to rotate this square, which is another way of saying we are going to spin it around a specific point. Let's think of this as a fidget spinner or a wheel. There is a center point that stays still, and everything else moves around it. Before we spin anything, we need to know where the anchor is. Looking at the graph, the problem tells us to rotate it about its center. Now if you look at the square ABCD, the center is that little circle icon at the point 30. This point will not move. Everything else will move around it. The question asks for a rotation of 1/4 of a turn clockwise. Now 1/4 turn means 90 degrees turn. So if the square was standing tall, it's now going to be lying down on its side. Clockwise is an indication for the direction the square will move, and this means it will turn to the right. Now, when you rotate something around a point that isn't 0, 0, it can look tricky. But here is the easiest way to visualize it. Since the shape we are rotating is a square, which means that all sides are identical, all we have to do is to imagine a line connecting the center, 3, 0, to point A, 1, 2. Now here is the trick. Rotating a square at 90 degrees is like placing a mirror at the center of the shape and looking at the reflection. Let's start with point A. We have that at 1, 2. Now let's imagine a mirror was placed vertically in the middle of the square. We are imagining the mirror there because we are rotating clockwise, this means to the right. so a prime or the reflection will be at 5, 2 now. Let's do point B. We have that at 5, 2. Again, imagine a mirror placed horizontally in the middle of our shape. Now, we placed it horizontally because we are still rotating clockwise, so our new points for B or prime B is 5 and -2. Let's do point C. We have that at 5 and -2. Since we are moving clockwise, we are going to imagine the mirror vertical again. So the reflection of point C on the other side would be at 1 and -2. Let's do our last point D. Again, since we are moving clockwise, to the right, we are going to imagine the mirror horizontally. So the reflection of point D on the other side would be at 1, 2. Can you see what happened? Our shape is still in place, but our points moved clockwise from one corner to the other corner. Thank you for watching, and see you in the next video. Alright, let's take a look at this geometry question. We are dealing with a rotation, which means turning a shape around a specific fixed point. First, we need to know which rectangle is the original and which is the rotated one. Going back to our question, you can see that the question mentioned that rectangle OSTV was rotated onto rectangle WQTR. This means that the original rectangle is OSTV and rectangle WQTR is the rotated image. Now, the easiest way to find the center of rotation, or the anchor point, is to look for a point that didn't move at all. Let's have a look at the names of our rectangles, OSTV and WQTR. Do you see a letter that appears in both? It's the letter T. In the diagram, notice that point T is a corner for both the standing rectangle and the lying down rectangle. Because point T stayed in the exact same spot while the rest of the shape rotated around it, T must be the center. Thank you for watching, and see you in the next video. Alright, let's take a look at this rotation question. Rotations can seem tricky at first, but once you see the pattern, they're actually easy to find. We are rotating points 90 degrees counterclockwise around the origin, 0, 0. Think of the origin as the center of a clock, and the point is the tip of the hand moving backward to the left. The question tells us that point A starts at 3, 0. Now we rotate it 90 degrees counterclockwise so it lands on point B at 0, 3. Notice what happened to the numbers. The X and Y swapped places, and since we moved into a new area of the graph, we have to check our signs, positive or negative. Now the question asks us to take point B, 0, 3, and rotate it another 90 degrees counterclockwise to find point C. When we rotate 90 degrees counterclockwise, use this formula. When rotating X, Y, the rotation points are negative Y, X. So for point B, our coordinates are 0, 3, so X equals 0 and Y equals 3. Let's start by swapping them, so put the Y value in the front and the X value in the back. 3, 0. Then change the sign of the new X value. Since 3 was positive, so it becomes negative now. Our new coordinates for point C are negative 3 and 0. Let's check our work on the graph. If you look at point B, 0, 3, on the y-axis and imagine pushing it 90 degrees to the left, it will land right on the x-axis at negative 3. So the coordinates for point C are negative 3, 0. Every time you rotate 90 degrees counterclockwise, you are moving one quadrant over. Point A was on the line between quadrant 1 and 4, B moved to the line between quadrant 1 and 2, and C finishes on the line between quadrant 2 and 3. Thank you for watching, and see you in the next video. Alright, let's take a look at this question together. The question asks, what is the image of point M under a rotation of 30 degree counterclockwise? Let's break this down into 3 easy steps. First, we identify our starting point, M, on the protractor. If you look at the markings, point M is sitting right at the 120 degree mark on the protractor. Second step is to determine the direction. The question says we need to rotate counterclockwise. Now, clockwise moves like a clock, to the right and down, while counterclockwise moves the opposite way to the left. So, we are going to move point M further to the left along the curve of the protractor. Now, for the last step, we will do the math. Rotation in this context just means we are adding or subtracting degrees. Since we are moving counterclockwise, increasing the angle from the right-hand start point S, we are going to subtract from the current position because the numbers on that inner scale get smaller as we go toward the left. So, point M is at 120 degrees, and we want to rotate it 30 degrees more towards the left, so 120 minus 30 equals 90 degrees. Now look at the protractor and see which letter is sitting exactly at the 90-degree mark. That's right, it's point K. Great job, and see you in the next video. Alright, let's take a look at this geometry question. It's asking us to perform a rotation, which is just another way of saying we are going to spin a point around a fixed center. Here is the step-by-step breakdown of how to solve this. First, we need to find the starting point of R on the grid. Look at the x-axis, which is the horizontal line. Point R is sitting right at -3. Now look at the y-axis, which is the vertical line. Point R is sitting right on the line, so its height is 0. Therefore, the original coordinates for our are -3, 0. For the second step, the question asks for a -90-degree rotation around the center O, the origin, which is 0, 0. In geometry, a positive degree means we turn counterclockwise to the left, and a negative degree means we turn clockwise to the right, like a clock. Therefore, we are going to rotate our point, R, 90 degrees to the right. There is a very handy rule for rotating a point by -90 degree around the origin. Take our coordinates x and y and switch their values. Next, flip the sign of the new y value. Let's plug in our numbers. The coordinates of point are -3 and 0. Switching them, we get 0 and -3. Now, flip the sign of the second number, so the -3 becomes +3. After we spin point R from the left side of the graph 90 degrees clockwise, it lands perfectly on the y-axis at the top. So our new coordinates are 0, 3. You can always double-check your work by looking at the graph. If you start at -3, 0, on the far left and rotate up and to the right by a quarter turn, landing at 0, 3 makes perfect sense visually. Well done! See you in the next video. Alright, let's take a look at this geometry question together. Dealing with rotations can feel a bit like trying to solve a puzzle, but once you know the rules, it becomes much clearer. First, let's look at what we are being asked. We have an original figure, the triangle in the top image, and we need to find its image after a specific transformation. In geometry, a half-turn means a rotation of 180 degree. Think about it like this. A quarter turn is 90 degree, like moving from 12 o'clock to 3 o'clock. And a half-turn is 180 degree, like moving from 12 o'clock all the way down to 6 o'clock. Whether you go clockwise or counterclockwise for a half-turn doesn't actually matter. You'll end up in the exact same spot. The second part is what trips people up. When you rotate a shape 180 degree, it doesn't just move, it also turns upside down. In the original image, the side of the triangle is on the bottom, and the point is facing up. After a 180 degree turn, everything reverses. The flat side will now be on the top, and the point will be facing down. Now let's check our options. We are looking for a triangle to be on the west side, and to be pointing down. Yes, it is the third option. By following both rules, we can see that the triangle has moved to the opposite side of the origin, and has been turned completely upside down. Now here is a tip. If you are ever stuck on a test, sketch a rough shape on your sketch paper, and try physically turning your paper upside down. That represents a 180-degree rotation. The way the shape looks when the paper is upside down is exactly how the image should look on your original graph. Thank you for watching.